All right, so as a reminder, I'm Thomas. I'm a master's student at McGill, and I work with Vicky Caspi and the CHIME collaboration. And today I'm going to be talking about some work on fast radio bursts, and in particular, our fast radio burst alert system known as CHIME FRB VO events. So there's a lot that I want to tell you and not much time, so I might rush a little bit, but I just want to cover all the key points so we know what we can talk about during the sci-a-thon. So first of all, fast radio bursts, as the name suggests, are fast. They're typically around a millisecond in duration. And when they arrive at the telescope, they look something like this black line here. They have this frequency-dependent dispersion that's a result of propagation effects as they travel from the source to the Earth. And if we undo that dispersion, we get something like this profile in the upper right. And the amount of dispersion is roughly equivalent to the distance that burst has traveled. So we know by de-dispersing that these bursts are coming from well outside the galaxy. In fact, one FRB was recently localized to a host galaxy at a redshift of about 1. So some of them are coming from cosmological distances. And after we de-disperse them, we get this profile. And what we're seeing in the profiles is a wide range of morphology. So you can have really narrow bursts. You can have kind of wide blobby bursts. You can have bursts with multiple components, bursts with scattering, et cetera, et cetera. So it becomes quite a difficult challenge to explain what sort of progenitor could be producing these. And yeah, at this point in time, we don't really know what's causing them exactly. Some hints that might provide answers is that we've detected about, or at least we've published about 1,000 FRBs so far, and the estimated all sky rate is about 10,000 a year. And we see that some of these sources repeat and at very highly variable repetition rates. So some of them only repeat once, and then some of them repeat thousands of times. And in general, that repetition is not periodic, although there are a couple sources that show periodic activity. So that's really interesting. But at this point, it's still a bit of a mystery. The best evidence by far for a progenitor has been a galactic magnetar, which was observed to have a high energy emission coincident with radio pulses that were FRB-like. And so that certainly motivates high energy follow-up. And there are also candidate progenitors that would have multi-messenger counterparts like gravitational waves. So how we actually detect them is through the Canadian Hydrogen Intensity Mapping Experiment, or the CHIME telescope. This is a transit telescope in British Columbia, Canada. It was originally a cosmology experiment, but it turned out to be a fantastic radio transient detector. That comes down to a few things. One is its large field of view, about 200 square degrees. And the other is that because of this kind of unique parabolic half pipe shape, or half cylinder shape, it's able to see an entire north-south strip of the sky. So as the Earth rotates, it scans the entire northern sky every single day. And it's also got a pretty ridiculous data processing backend. It goes through a couple of 100 petabytes a day of data. So in terms of actually communicating that, we now have an observatory that detects FRBs. We know that high energy follow-up and multi-messenger follow-up is crucial. So the first step towards a VO event system was defining a VO event standard, and that was done by Emily Petrov. And basically what it comes down to is that FRB VO events should be one of the following 4. So detection, meaning a new FRB source; subsequent, a burst from an already known source; retraction is just a false positive; and an update, which is sort of a flexible VO event that allows updated parameters like localizations. And then crucially, every VO event includes sort of 2 sections, one describing the host observatory and their FRB search pipeline, and then one describing the burst metadata, things like localization, time of arrival, signal to noise, etc. So in terms of the actual workflow of this VO event system, we start with what I call the trigger phase, which is right here. So it includes some host observatory like CHIME issuing a detection of either a new source or a repeater. And the other possibility is some operator, basically some human intervention, issuing a retraction or an update on an already broadcast VO event. And that goes to this VO event server, which crucially validates that data and ensures it follows that VO event standard. That's important because when other observatories might install such a service, we want to make sure that all the VO events, the FRB VO events are consistent amongst observatories. And so once that data is validated and follows the FRB standard, then it's saved to a database. Optionally, we can also submit to the transient name server. And then in terms of actually getting that information to subscribers, we have one of 2 types of reports. So we offer machine readable XML reports through the Comet broker. And we also offer human readable emails. I'll include a link to that at the end. So a quick overview of sort of the CHIME VIO event service so far. So it became public in October of 2021. And as of June this year, we've published about 1,750 VIO events, which just to put that into perspective, earlier I said there are about 1,000 FRBs published so far. So this is the largest public collection of FRBs already, which is kind of cool. We publish about 2 FRBs a day, or 2 VIO events per day, I should say. And as you can see from this pie chart, that's about 6% retraction rate. Although that has probably come down due to some recent changes to our known source sifter. So I'd guess that it's below 5 now, but anyways. In terms of latencies, just to be clear, I'll define the latency as the point from when we detect it at the telescope to the point we send it out from our Comet broker. So that doesn't include, any sort of network delays or broker delays after that. But that latency is typically around 12 or 12.5 seconds for detection and subsequent events. And then our retraction events have much higher latency, because those involve some sort of human intervention to look at the event. So those are typically around 24-hour latency. Okay, so the engagement from the community has been fantastic so far. We have over 100 groups subscribed to VIO events from all over the world and all different levels of academia and some amateur astronomers as well, which is really exciting. I guess the main result of this whole project is that now coordinated FRB detections can be done within a few seconds, as opposed to before when it was through ATELs or publications, which might be days or weeks. So that's kind of the key result. But also we've had some really exciting instances of follow-up from Swift. Thank you. And also one event that was detected by CHIME and then localized by the Deep Synoptic Array in California. So that was it just starts to show the exciting potentials of FRB VIO events. So I'll just mention that we also now, we have a public webpage that describes sort of summary of the service. It allows you to submit a subscription request if you want to subscribe to FRB VIO events. And we also added a database of all broadcast VIO events and a JSON file you can download and play around with.